Before we begin, we're about to enter p-valley. It'll be useful to keep our heads up, otherwise we'll be drowning. A regular p will stand for the population proportion. This is unknown to us. P0 will be used for the null proportion, our guess of p. P hat is the sample proportion. This is what we measure. Finally, the p-value is the area under the curve. You might want to write these down and keep a little list handy. We almost always deal with the sampling distribution. Here's a graph of a population distribution of income. This is a highly skewed distribution. Each x value represents an income from the population. So this is the percent of people who make X dollars. Because of the shape, we would need to do some serious math to find the area under this curve. Instead, we consider an abstraction. Think about taking 1 trillion samples and making a distribution of the average of each. That's the sampling distribution. Each x value now represents the percent of samples that have an average income of X dollars. The sampling distribution is normal, and we have formulas to compute the mean and standard deviation. In practice, we'll never take more than a single sample. However, we will consider this sample to live in the sampling distribution. Then we'll calculate the probability of finding that sample given our hypotheses. If that probability is low, we can say our hypotheses were wrong, which is good. For proportions, the sampling distribution is n of p, the square root of p times 1 minus p over n. The p is the mean, and this is the standard error of the sampling distribution. Standard error acts essentially the same as standard deviation. We won't actually have this p, so use one of these p's in order, stopping here. The p-value is different. The z-score is then p hat minus p0 over the standard error. If we were computing a z-score, we'll always have the null. Finally, this only works if both n times p is larger than 10 and n times 1 minus p is larger than 10. These are the assumptions for the sampling distribution of the sample proportion. Let's do an example. Suppose we have p0 equals 0.6, n equals 100, and p hat equals 0.72. Find the probability of a proportion larger than 0.72. Draw a picture. Label the mean in the sample proportion. We want to shade to the right. Find the z-score. Use this and the z-score table to find an answer of 0.0084. This is a very small probability, which means the null was probably wrong. Let's use these same numbers, except make p hat equal to 0.53 and find the area to the left. Again, draw a picture, shade to the left, find the z-score, and use that to find the area. This time it's 0.0808. This is fairly large, and we can't say the null is wrong. Finally, given n equals 100 and p hat is 0.72, estimate p by finding cutoffs for 95% of the data. Here's a picture of what I want to find. We'll be working in reverse. The z-score for an area of 2.5% is 1.96. We have plus or minus because we're on both sides of the mean. Set up the z-score formula and solve for p. I get the following interval, 0.63 to 0.81. This is the 95% confidence interval. I am 95% confident the population proportion lives in this interval. We'll go more into depth in this later.